Good morning, good afternoon, and good evening, everybody. It's 3 p.m. At least here in Europe, in Darmstadt, where I am. Let's as always start this short course today. So I introduce myself. I'm Federico Fierli from EUMETSAT, I'm senior scientist. And today we will work together with Sabrina Szeto, that you see here. Hello, Sabrina, and Carla Barroso. So Sabrina works with us in EUMETSAT and is a data specialist, and Carla is also in EUMETSAT and also is a satellite application specialist. And the three of us will guide you today in discovering the existing and the next generation satellite product for wildfire monitoring. So today is a quite is a quite varied short course because there is a very important practical part with the Jupyter notebooks and books. So you will see a lot in terms of practical use of the data. What we will have. So we have a first introduction. It will be given by me. Then Sabrina will take you to familiarize with the practical part. Then you will have Carla that will focus on how the satellites they observe the key variables for monitoring and assessing the impact on the wildfire. And then you will have a second part that is really focusing on the hands-on satellite products. So you will have really the chance to touch on the data and also to have tools to work on the data after this course. So let's start just with some intro. So who we are, what is EUMETSAT, what is the program Copernicus. So EUMETSAT is a European based organization that has the task to monitor weather and climate from space. So we maintain satellites, we distribute data, and we also ensure uptake of the satellite data sets, and we also do training like the one here. Copernicus is the cornerstone program of the Commission of the European Union, and basically is a program that deals with environmental monitoring for Europe and worldwide. So it's a program that does both observations and infrastructure. So the dimension where EUMETSAT is more involved with the so-called, with the famous or probably quite known Sentinel satellites, and also the services that are, for instance, implemented by our colleagues in ECNWF. You will hear about that, but also by the European agency. So basically is a program that has the aim to provide the best information for the next decades in an open way. And this is extremely important for us for improving the information monitoring and forecasting capability. So let's go on the wildfire. So wildfire, we know what we are talking about. Is a complex phenomenon. Is a natural phenomenon, but for sure has many relations and is strongly impacted by the human activities in different ways. So the first one is, of course, the ignition, because the wildfires are very often ignited by human action. Not only by lighting, but the presence of human and the society is crucial for this. But also wildfire are favored. The ignition is favored by background conditions like the weather conditions, for instance, presence of wind, the state of the vegetation, the temperatures, and so on. And we know that all these factors are influenced by the human activities and are influenced by climate change. So is a complex scenario that also touch enormously the human dimension, and is touching more and more the human dimension. So here on the left you see a photo that was taken last year during the fires. This is the fires in Greece that was a quite important and large event at the end of July, early August, and you see that the presence of fire is really is really closer to the human environment. And below here we see an image of from North Africa. Is in Kabylie during the same year, almost the same period, and you really see that there is really the question on how to manage the fire, and not all the countries or not all the context have a level of preparation, like for instance monitoring, the capability to forecast, the capability to prevent. The observation, we have mentioned the observation and the forecast. We start from the idea of requirements. So basically, this is a slide in French because it was given in a French event. So we have different scales. So the first one is at the fire scale, and here I report the schema that is implemented by the French Ministry for Environmental Protection. That tells how, for instance, the firefighter and all the chain works in order to monitor and to fight the fire. So using, for instance, decision, data for decision, control, and intervention on the ground with helicopter and airplane. And in fact, what is needed here is really to understand which is the level of the risk, so to have the possibility of an early warning. This comes from observation, weather parameters, and here Earth observation have a role. Then you have the management of the fire itself, so with the intensity, how it develops, and here you really need the data in real time at very high resolution, because often the fires, especially in the Mediterranean basin, are not so large, even if part of them are visible by satellite, and the data sets have to be interpreted in a very easy, straightforward way. So the decision has to be very fast. And then there is the question of the impacts. So for instance, quantifying the extent of the burned area, the pollutants, the amount of pollutants that are, for instance, emitted in the atmosphere. Then there is a global scale, so a climate aspect, and the climate aspect is getting more and more important. Here, I mean, there are three representative elements. So the first one here on the left is the condition of dryness. So is the anomaly in terms of dryness. So the red, the drier, the blue, the wetter. For Siberia in the last 2 or 3 years. So this comes from one Copernicus service, so C3S, and we see that in fact the unusual and the increase of fire events in Siberia and in northern Eurasia, that were regions where they had much less fires than what was observed in the last couple of years, are really related to weather, to induced weather conditions that are induced, also changed by the climate change. Then at the center you have an image from the Sentinel-3 satellite you will hear about Australia. This is 2020. We all heard about that, and these are single fires during the season that had an enormous impact, not only in terms of burnt area, of impact on the ecosystem, but we now know also that had an impact in terms of the global composition of the atmosphere. I mean, due to enormous amount of pollutants and also particles that have been thrown in the atmosphere. And here is that one last example is about Africa. And we see here the fraction, the probability of having burn areas in the different regions. So we see here the region in Central Africa that is one of the principal, probably the principal region of wildfire in the forest, but also the region of savanna. And Africa is, in fact, the region of savanna is an open scientific question with the point of the change of the total amount of vegetation. In fact, we know that the amount of vegetation, the amount of burned area is decreasing in the last 20 years, and that this is mostly related to the decrease of the amount of burnt area that is observed in the savanna. But there is still the question on how well, for instance, the Earth observation are capable to capture that. But in any case, the main points at climatic level, and here I just report A very strong, short synthesis from the IPCC is the fact that the climate change is more and more important for to understand how the fire will work, what is the fire regime, and also the increase of the risk and intensity. The length of the fire season is increasing between 79 and 2013. So based on the data, and this is also extremely important, not only in terms of the longer risk, but also in terms, for instance, of the management. And then here we have at the climate level to understand this, to monitor this, to evaluate the impacts. We need global measurements. The measurements have to be continuous, have to be uniform, so have to be comparable with the past, and have to be long-term. But we also need measurements that keeps as much as possible the resolution, really, in order to aggregate information that very often happens at very small scale. So we have mentioned Earth observations. I will just provide you a small intro on what we are talking about when we talk about Earth observation. This is the first image of our planet from, let's say, outside the atmosphere. It's not precisely outside. It's 24th of October 46. It's from the V2 rocket, so it was used in the Second World War, and I mean was used in that case for the first imagery. So it's about 80 to 100 kilometers. So it's a region that we consider out of the atmosphere, and from them we have made many steps ahead. So, for instance, we were able to work with satellites, and also, for instance, to develop techniques that allow to measure pollutants. So not only to have images, but also to have the possibility to infer about the composition of the atmosphere. And these are two visual examples, for instance, of troponin, nitrogen dioxide, and ammonia from gases. But let's go back to our fire story. So I will just introduce you to basic geometries that you will hear about of observation from the satellite. So the first is the geostationary. The satellite is observing always the same face of the Earth, and that is typical for the MEEO, second and third generation, the measure over Africa and Europe in our case. The point is that they always observe the same faces, so they have a continuous time covering, so there is a high temporal frequency, but they observe the same places, so you need a different geostationary satellites to cover the whole Earth. And also there is a geometry deformation in high latitudes, but also there is a problem of the fact that the geostationary orbit position is farther with respect to the polar one, and then the signal to noise ratio is lower. So you have observation that have less quality in terms also of imagery, but also of composition. But for instance, you have the possibility to have a continuous coverage. Here is every hour is the evolution of the fire radiative power that you will hear about, and how this change in that case in Africa. And also to have images like this, so imagery that combine, for instance, cloud with cumulonimbus and with the smoke plumes. The second geometry of observation is the polar. Has the possibility to go to also to high resolutions. Has a limited temporal sampling, but we have, for instance, the possibility to accumulate data. And this is an example that comes from our colleagues, our friends at NASA. So it's a composite of MODIS that we will also see later, and of imagery. So you see, for instance, the coexistence of fire, that are the red dots, with the smoke plumes that are associated, for instance, here to that regions. And here again is an example on how to aggregate the data sets from polar orbits, and that this is the example of Copernicus 5P, Sentinel 5P. So what is remote sensing? Just to give a few simple definitions. So basically we use artificial devices, not our eyes, to observe things from a distance without disturbing. So it is possible to measure things on spatial, temporal scales, but also spectral parts that allow, for instance, to access to the role and to the impact of to the role of chemicals. And also it gives the possibility to observe globally our environment without for instance, the prejudice associated to national boundaries and so on. So it is also very important to observe phenomenon that happens at global or continental scales. basically is a remote sensing is an observation of the electromagnetic spectrum from space. So you have mostly passive sensors. This is what you will hear about, that will go from the ultraviolet to the microwave. And in that case, in our case, you will see visible examples, infrared and ultraviolet, to see how these cover the different part of the spectrum. And also there is use of active sensors. The measurement concept, I mean, basically, you have the satellite here, and in the case the satellite measures the reflected radiation, the radiation comes from the sun, then is scattered into the atmosphere, is reflected from the surface with different property of reflection, and then interacts inside the atmosphere. For instance, when you have a layer of aerosol here, like that one, or a cloud, you have an interaction with the radiation that brings to absorption, a change of polarization, and also re-emission. And this type of signature is observed by satellites. So this change of the reflected radiation. When you have in fact, the chemical species, you have a similar phenomenon happening. So you have absorption and emissions by the atmosphere, depending in a region of the spectra that it depends on the stoichiometric formula, on the structure of the chemical. And based on the same principle, it is possible to retrieve information on the whole column for the concentration of species. And this is what we define the vertical column density. So basically, the satellite, they observe what happens in a whole column, atmospheric column, in different places, of course, of the planet. I won't go ahead on this. This will be Carla that will show you how we observe with the smoke. I just want to introduce you to concept before leaving the floor to Sabrina. So we will focus during this short course on one event that are the fire in Greece and Turkey 2021 that were important in terms of impact, as we see, of human impact, but also in terms of extent and in fact emissions at the level of the Mediterranean basin. So with the fire plume dimensions here of the order of magnitude of the dimension of the island of Rhodos or half of Cyprus. So we are really talking about intense emissions due to the intensity of the production and also the duration. So we will see what is a so-called data value chain. So an ensemble of data sets, an ensemble of products that go from the prevision to the risk assessment and to the observation from satellites. I mean, here is a representation of an Indian proverb. So the point that if you want to observe or characterize a phenomenon, I mean, you can only observe or have parts of it. So basically, the objective of the concept of the data value chain is really to compose the different parts and to arrive to an integrated system. So using satellite data and models that integrate the satellite data, really going from the forecast. This is an example, for instance, on a CNWF forecast, going through the estimate of the emissions that can come, for instance, in that case, from the CAMS service. So just a few examples. The risk evaluation the first part makes use of the forecast. This is an example of the CNWF forecast. So we have a forecast of weather. Then we have dryness that comes from satellite, and then there are services like the LSA service or also the emergency management that combine these elements and provide a fire risk map. And this is the fire risk map for the period of August 2021, with an extremely high risk in Greece and in Turkey and also in several parts of South Italy, due to the combination of dryness, so how much the condition of the terrain are prone to ignition, and also to weather condition. Then you have the phase of monitoring, and this is where we will focus more today. So how to observe the active fires, how these active fires produce plumes, particle plumes, burned mass plumes, and you can observe them here. This is in fact the detail of what here has happened in EMEA. This is from MODIS, that is a proxy of what will happen with the next satellites, and that this is, for instance, Sentinel-3. Both of them will be object of discussion today. And here is an observation from Sentinel, Sentinel-5P in that case, of the whole amount of absorbing particles or absorbing aerosols. So here you clearly see the signature of the fires, but with a quite strong background and the mid-range transport of the plumes. The system evolves. So we have now a series of satellites, of instruments, but also very importantly, we have new generations. So we have mentioned the Sentinel. So we arrived now Sentinel 1, 2, 3. So we have now Sentinel-5P that is flying, but we are really awaiting Sentinel-4 that is geostationary, and the Sentinel-5 that will be useful for the composition. And also this goes together with the different missions that comes from EUMETSAT. So what we'll talk in a second is the MEEO third generation. So the new geostationary satellite, it goes together with the new polar. And if you see here down, this is the time span, and these are programs that really encompass the next 20 years. So these are programs that really aims at having a long-term capability to support, to observe, but also, for instance, to build a long-term observations. And also there is the role of the European Space Agency with the Earth explorers that are really let's say, improving and providing new concept and very, very advanced observations. So basically, with the satellite, we really can characterize, as we say, the presence of pollutants, the burnt area. We can also combine images and data really to go and characterize the fires, the wildfire in that way, and also they enter into the models and into the integrated service like CAMS to for instance have an evaluation of the tendency of emissions. We have mentioned the MEEO third generation. So this is a new series of satellites. The launch of the first one is planned for November this year. So is really about to arrive. We are really eager of it, and is a series of geostationary satellites that have different capabilities, imagery, but also the possibility with Sentinel-4, and this is planned for 24, to measure the composition and also layers of the atmosphere. It is the first time, and the first point about imagery you see here. So MSG is what is actually flying. This is Portugal, south of Portugal. This is the region of Algarve. And you see how a fire here, this fire X in day N, is observed. And here you see with the new instruments, with the higher resolution, we have the possibility to observe the fire with much larger level of detail, with a much better geographical identification. And this is a proxy. So these are existing data sets also coming from MODIS that will be soon phased out, and is also polar. So we'll have the possibility to have this observation in continuous way, 24H, and this is important. And this is still how the combination of the fire together with the visual observation of the plume. This is an example from GOES that is in the US, and is how the new MEEO third generation may observe fires in our disk, so Europe plus Africa. We have mentioned the Sentinel-4 that will be on the next step for MEEO third generation, and our observation of atmospheric composition from geostationary. So we can have what we call a sort of chemical weather, so the possibility to observe hour by hour the evolution, in that case, of nitrogen dioxide. And this is an animation with simulated data for 1 day, and this is the day of the event of wildfire in Greece. And then, for instance, here you start to see the effect of pollution here from Athens. You have the effect of pollution from the ships and from the main towns here in the Mediterranean area. But then what we expect is that once you have a fire that is a strong emitter of nitrogen dioxide, you may observe this type of signature, and then you see the hourly evolution in the case of the plume that is produced in that case by the area fire. So we are really excited about this opportunity. If I am able to go on the next slide, okay. Okay, so basically I stop here. So it's everything I wanted to say. I give the ball to Sabrina that will start you to introduce on the case that I have mentioned. So on the 2021 case in the Mediterranean, and also start to prepare the practical part. Okay, the ball is to you, Sabrina, and thank you very much for the moment.
Thank you, Federico. So I saw a lot of people also started to introduce themselves in the chat, and I would like to also invite you right now on Slido we actually have some icebreaker questions that we will use to get to know you a bit better, and also to get to know what your expectations are for this course. So the first question we have is, where are you joining us from? And I welcome you to type in the country you are located in right now, just to get a sense of how to use Slido. So for those who are new to Slido, you can just go to slido.com and type in the hashtag EUMSC34. This is the event code that will take you to this Slido. If you have a smartphone, you can also take a picture or scan the QR code on the top left of the screen that will then also take you to this Slido. All right, so far it looks like we have people calling in from all over the world, from many different continents. Germany, France are the two big countries on the screen right now. We also have India, England, and Greece and Poland as the next biggest countries. We also have people calling in from Asia. Vietnam is one of them, one of the countries, Indonesia, Israel, in the Middle East. We have South Africa. So I'd just like to say a big welcome to everyone also calling us from Mexico, Colombia, USA, and Ivory Coast. A big welcome to you. So our next question is, how familiar are you with remote sensing and satellite data? So feel free to answer whether you feel that you are a beginner, an expert, or someone who has an intermediate level of familiarity with remote sensing or satellite data. Okay, so far it looks like half the people in the room who have responded are intermediate users of satellite data, and we have a spread between slightly more experts than beginners. So it sounds like most people have used some satellite data before. So that's really good. And I'll make sure that for those who are beginners, we will also explain things so that you can understand what's going on. All right, let's go on to the next question. The next question is, how familiar are you with Python? So we will be using Python libraries or the Python programming language to do a lot of the workflows or the processing of this data that you'll learn about today. And so far, it looks like most people are beginners, and the other part, well, actually, 43% are beginners, and the rest of the people in the room have either an intermediate or expert knowledge of the language, which is good. So I will keep things at an intermediate level to make sure that our beginners also are able to understand what's going on. Yeah, thank you. And let's go to the last question, please. So the last question is, at the end of this short course, what would you like to have learned? And I see some people have interests in technical skills such as Python and understanding how to use Jupyter notebooks. Others are looking at more specific topics such as how to access and interpret satellite data, what kinds of inputs are out there, how can we use satellite data for wildfire monitoring and carbon impacts, how to make an alert system. Great, how to use EO data in Python, accessing MTG fire data, forest fire monitoring, how to work with technical guides and do some networking. And some have more regional specific questions relating to how you can apply products generated over Europe to perhaps using the same methods for India and the USA. Great, awesome. And I think we will definitely be covering a lot of these topics in the demonstration today. So thank you so much for sharing your input and what you want to learn. And thank you also to Rosa, who is providing technical support today. And I would also like to introduce Julia Wageman, who will also be answering your questions later on. So if you have any technical issues while you are working with the Jupyter notebooks, please send her a direct message in the chat, and she will be able to help you work with them. So I will now share my screen, and at the same time, I'm going to paste the link to this website here. So if you click on the link that I just pasted, it will take you to firebook.ltpy.atomplatform.eu. And this is a Jupyter book, which is made out of different pages, which actually are in themselves Jupyter notebooks, to create this website that provides you a way to learn and understand a bit more about how we can monitor and predict fire risk, active fires, as well as look at the impacts from wildfires using the upcoming MTG or MEEOsat third generation, as well as the EPSSG or the EUMETSAT Polar System second generation satellite missions. So the first thing I would recommend that all of you do is to go and click on this link here called register. And this register link will take you to a page where you can make a new account. So if you have attended a workshop before and you have already created an account here in the past, you can use the old account you have and just log in with the username and password. If you are new to this, please click on sign up new account, which will take you to this form. And you will need to fill in your username and password that you want to use, as well as some information such as your email address, your name, your country, and then you have to accept the privacy and the terms and conditions before saving. After you click save, you will receive an email with information for how to open your account and validate it. So once you have filled in this registration form, click save, and then wait for a few minutes and check your email to then get started with the account. So for those of you who already have an account, you can just log in, and this will take you into this page here with 3 images, and then you know you're logged in. So at this point, just stop there and then go back to the Firebook. So that's just to make sure that you have logged into the platform. So now I'm going to provide you an overview of this Jupyter book. And as you can see here on the left-hand side of the screen, there is a panel that you can explore. So we have 2 case studies. As you can see here, one is based in the US. These are the California August complex fires in 2020. However, today we'll be focusing on the Mediterranean fires from the summer of 2021, particularly the fires in Greece and Italy. So this is an image showing the wildfires on the island of Evia in Greece. And we will be focusing on this case study to also showcase some of the new capabilities on the upcoming instruments. So this is an overview of some of these instruments that we have featured in this case study, as well as several complementary or proxy data sets that we will also be looking at. Here are some of the data providers. We are using a wide variety of data for this case study. And another note is that to help those who are a little bit new to Python, we are actually using several predefined functions, which you can see here. So for example, one example is a function called visualize p-color mesh. And if you click on this link, it will take you to this function that has, which is basically a block of code. And what it does is it visualizes some data and plots a map. And it makes it a bit easier because as a beginner, all you have to do is to type in some of these arguments into the function without having to type out all this other code. So I encourage you to take a look also, if you're interested, at all the functions we will be using in the case study. So without further ado, I'm going to click on the part 2 here, monitoring active fires with next generation satellites. This is the second part out of a 3-part case study on the Mediterranean fires from 2021. The first part has been covered in a previous webinar where we looked at pre-fire risk and how we can forecast pre-fire risk. Today we'll be focusing mainly on monitoring the active fires, looking at active fire radiative power, as well as smoke. And if you're interested in looking at impacts such as burnt area or calculating a burn severity map, you can take a look at the third part. So the case event, we had a long period of warm and dry weather in the summer of 2021, and that led to high vegetation stress and a lot of fuels were accumulated. The fires that broke out then in Greece mostly occurred on Attica, Olympia, Messenia, and Evia. And the fires on Evia were particularly devastating because they destroyed over 125,000 hectares of land, and 2 people passed away from the fire. In southern Italy and Sicily, we also had several fires break out. In Calabria, there were actually these ancient beech forests that are a UNESCO World Heritage Site that were being threatened by the fire. So wildfires cause both damage to human infrastructure, but also leave a lasting environmental impact. So as you can see here now, we have introduction to MTG as well as EPSSG. And Federico provided already some background about these upcoming satellites. But if you have more interest, feel free to click on the link and you can see more information about these particular upcoming satellites and instruments. So in this case study, we are covering several upcoming instruments. There's a MET image from METOP-SG, the flexible FCI, the flexible combined imager, FCI, the Sentinel-5 ultraviolet visible near-infrared shortwave UVNS spectrometer, followed by the Sentinel-4 UVNS. If you see METOP-SG, this is actually referring to EPSSG. So they are connected terms and you will see them being used. One describes the program, one describes the series of satellites. And so this is why you will see them. So as Federico mentioned, we're working with proxy data, and in general, when we do not have existing data coming from these new satellites, what we're doing is looking for other instruments that are already in orbit that we can use as a proxy. So these real data sets are from existing precursor instruments that will be then useful for you to have a view into what these new data sets will be like. So I will be going through several of these in more detail later on. I will just quickly show you a few of the products before turning it over to Carla to tell you a little bit more about the data products involved. So here we have a detection of plumes using a false color composite with the Sentinel-3 ocean and land color imager data, Sentinel-3 OCHI. And the recipe for this false color composite is red, green, blue, and channel 17, channel 5, channel 2. So what this means is that the red channel was assigned to channel 17, which has 865 nanometers of wavelength. The green channel was assigned to channel 5, 510 nanometers. And the blue channel was assigned to band 202, which has 412.5 nanometers. And then this provides you with a false color image that allows you to see healthy vegetation in green and burnt areas in black. And you can also see these plumes of smoke that are rising from EVIA. There's also a small plume here, but it's not so visible on my screen, in the southern tip of Italy. But here you can see quite clearly that there's a plume of smoke here from Greece. Then besides smoke, we can also detect active fires. And so we have two products here in the case study. Today we'll be focusing on the proxy data from the MODIS fire radiative power pixel dataset. And basically what this allows you to see are the fire radiative power over certain points. As you can see here over Greece in Evia Island, it is red or dark red. So anywhere between 80 to 500 megawatts. CAMS GFAS is another source of fire radiative power data. And once again, you can see these high fire spots, active fires being present here in Greece, but also in the southern tip of Italy. You can also see several fire spots. And then also actually in Turkey, there are some fire spots that are visible. We will also be looking at two products from Sentinel-5 in this case study. We have the aerosol index from 380 to 340 nanometers, and the ultraviolet aerosol index, where you see the yellow, that's around the background, that's the background values around 1 to 2. Where you see these darker brown areas, this is where you have an index value of 4 to 5 or even 6, indicating that there are strong aerosols being present, strong absorbing aerosols present here. And they again correspond to areas where there are active fires. If you compare these active fire spots before, you see that these high UVAI areas are also corresponding to these active fires. Sentinel-5, the UVNS instrument, also provides information on carbon monoxide. And this is Sentinel-5P tropomi data that we're using as a proxy. And again, you can see high levels of carbon monoxide being emitted from the areas, again, corresponding to our fire hotspots that we saw earlier on. Federico already showed this animation, which is the notebook that shows simulated Sentinel-4 nitrogen dioxide data. And you can take a look again and play this animation to see how, as the fires progress, there is a large red spot that appears over the Greek island of Evia. And for each figure, at the bottom, we have a link that takes you to a separate page, which is a notebook that's from a Jupyter notebook that then shows you the step-by-step process of how we generated these figures. But before I jump into this, I'm going to turn the mic back over to Carla Barroso to tell us a bit more about the different data products. Carla, please. Thank you.
Thank you, Sabrina. So I'm starting to share my presentation. So I will briefly explain some details on how these key products to monitor fires can be retrieved from satellite measurements. So I start with the fire radiative power. And this is a product that has been developed for a Fierli sensor on board MSG. MSG was actually the first geostationary satellite providing us observation data to be used to estimate this fire radiative power, which gives not only the location of the fires, but also the rate at which fires are emitting thermal radiation from the burning vegetation and or organic soils present within the pixel. So in other words, we have not only the location of the fires, but also their intensities. With this geostationary data that provide us high frequency observations, we are able to monitor fires throughout their life cycles, as illustrated in this figure on the right, showing the strong diurnal cycle of detected fires over one day in Southern Africa. And we see that the peak of the diurnal cycle generally occurred earlier in the day for higher FRP fire pixels. Despite the relatively coarse spatial resolution of these instruments placed on geostationary orbits, they are able, specifically speaking about Fierli, it is able to detect extremely small fires, subpixel fires, and allow to detect or to estimate FRP values as low as 30 to 40 megawatts. For the future, as already anticipated by Federico and Sabrina, the FCI, the imager on board MTG, will enable to provide FRP with a better also a special temporal resolution, but also spatial resolution. And we will have an increased sensitivity to smaller fires, given the smaller pixel area. And we expect that the radiometric enhancement of the fire channel will also enable us to get more fire detections without pixel being saturated. So basically, and making it very simply, the fire radiative power computation relies on the mid-infrared method that assumes that the FRP is proportional to the difference between the observed fire pixel radiance in the mid-infrared channel, this is the 3.9 micrometer channel, and the background radiance that would be observed at the same location in the absence of a fire. And this background radiance is derived from the set of pixels classified as cloud and fire-free surrounding each fire pixel. And why do we use the mid-infrared channel? So this is a basic physical remote sensing. This figure shows the spectral radiance emitted from black bodies at different temperatures. And we see that the peak of emissions occur at different wavelengths, which are, these wavelengths become shorter as the temperature of the black bodies increase. And so we have, for instance, that for the typical temperatures of Earth here in the red curve at 300 Kelvin, the peak of emission is around the long wave thermal infrared channel, 10.8, and for instance, for the case of the black body at the temperature of typical temperature of the sun, this emission is observed at much shorter wavelengths on the solar domain, and more specifically on the visible range between 0.4 and 0.7 micrometers. For the case of fires that have typical temperatures ranging between 700 and 1000 K, the peak of emission is around the 3.9 channel. And this is one of the reasons that this channel is used for fire detection. So fires produce smoke and trace gas emissions, and we are actually able to visualize smoke from the satellite images. And here is the very well-known RGB, the composite that takes into account solar channels. So this is an example of true color RGB from MODIS sensor on board Terra satellite. This was for an event that took place on August 2016 over Madeira Island in the Atlantic. And here is the recipe for this RGB. And so with this combination, we can easily see the smoke from the fires. And this example is from MODIS because we actually currently don't have the chance to produce this true color RGB from MSG, but this will be possible with the new imager on board MTG. These 0.5 and 0.4 channels will be new, and we will be able to produce this true color. So we will be able to look at the planet as we would do it with our eyes. That's what it is. Why is it called true color RGB? But okay, so this is a way to monitor smoke, but we are actually looking only at what the satellite measures. So we are not actually deriving any physical property. But can we quantitatively measure aerosols and trace gases? So all satellite remote sensing measurements of the troposphere are based on the use of electromagnetic radiation and its interaction with the constituents of the atmosphere. In this case, we are using passive instruments. So this means that we will rely on the information that is reaching the satellite sensor. And this can be either from, so generally speaking, not only considering aerosols and gases, what reaches the satellite are solar reflected radiation or scattered, and also radiation that is emitted on long wavelengths. So how do we measure these physical constituents, or the aerosols with satellite instruments? So we will use the fact that we know that radiation interacts with these constituents of the atmosphere, and by the aerosol or gases will leave spectral fingerprint in the radiation by either absorption or scattering. And putting it very simply, if we know what we would expect with no effect of this attenuation in relation with what we really measure, we can derive retrieval algorithms to compute these physical quantities. So we basically go from level 1 to level 2 products. And one of the most well-known aerosol products is the aerosol optical depth, or aerosol optical thickness, which is a quantitative measure of the total aerosols in the atmosphere, and it is obtained by the accumulation of the aerosol extinction at all atmospheric levels, from the surface to the top of the atmosphere, from scattering and absorption of the visible light by the aerosols. This AOD is wavelength dependent, so often products give AOD, for example, at 550 nanometers, and it has the drawback that it's not possible to derive this quantitative in regions with clouds. And we need to also take into account that the AOD informs us about the total load of aerosols, but it does not inform about the type of aerosol. And this product is available from several instruments and wavelengths. Here I have put an example of AOD at 550 nanometers from MODIS that uses this deep blue algorithm. Another very well established data product that has been calculated from several different satellite instruments spanning a period of more than 40 years is the aerosol index. This product uses ultraviolet wavelengths from 340 to 380 nanometers. And it is sensitive to absorbing aerosols, so not only smoke, but also to dust and volcanic ash. This figure here shows the UV aerosol index on the 10th July 2021, measured from the troponomy instrument, which troponomy stands for tropospheric monitoring, which is the satellite instrument on board the Copernicus Sentinel-5 precursor satellite, so Sentinel-5P, which is the first of the atmospheric composition sentinels launched in 2017. And we can see that this product provides a complete view with no gaps, so it is not disturbed by the presence of clouds. And from this figure, we can see that there is some Sahara, so I will point here, some Sahara dust flowing through the Atlantic, but also biomass burning over Canada. So this this product actually does not, so it allows us to follow the smoke plumes, but it does not provide the quantity of aerosols. So this should be used in combination with the AOD, so the product I just mentioned. And so we have, so I have talked about the monitoring of this aerosols, of this fine particles that constitute the smoke plumes, but are also emission of trace gases. And among the trace gases that are released, the carbon monoxide and nitrogen dioxide abundances can be very high. And there are great variety of satellites that are capable of measuring these quantities. One is the YASI. So the YASI is the infrared atmospheric sounding interferometer instrument that is on board the EUMETSAT polar orbiter satellite, METOP. And this YASI measures the infrared radiation at several wavelengths. And so it is able to provide an estimate of the total carbon monoxide amount. And here is an example of of a daily composite of total carbon monoxide for the 8th March 2017, and it comes in a number of molecules per square centimeter. And the future YASI and G on board the METOP second generation will ensure continuity to this YASI instrument on board METOP. And on this image on the right, there is an example of NO2. So the NO2 total tropospheric NO2 column. This is for year 2019. And this is obtained from Sentinel-5P. and this is the precursor for Sentinel-5 instrument that will also be dedicated to atmospheric monitoring, and it will be carried aboard EUMETSAT, MEEO second generation. I think with this, I will pass the ball to you, Sabrina, to continue with the hands-on.
Thank you, Carla.
Thank you.
So for those of you who might have questions right now, I invite you to always go back to Slido and type your questions there. We will make some time for questions at the end of our session today. So as you listen to what we're saying, if a question comes to mind, please just go directly to the Slido and type in your question. Then we will get to your question afterwards so you don't forget it. So thank you again, Carla, for this great presentation and for giving us an overview of some of the data products that we will look at. So I will begin first here with the Sentinel-3 Ulchi composite. If you click on the Sentinel-3 Ulchi link over here, it will take you to this page. And on the top of the page in the Jupyter book, there is an orange box that says hint. So if you go ahead and click on execute the notebook on the training platform, this will actually take you into the FIRE platform that you have just registered for. So if it asks you to log in, type in your username and password. For me, because I already logged in just now, it takes me directly to the notebook over here. So the notebooks in this platform are actually a mirror of what's available on the FIRE book. If I go first to this folder on the top left corner of this left panel, it will take me to a directory that shows all the different folders that are available. So as I mentioned, in the FIRE book, there's 3 parts to the case study. If you open any of these notebooks here, it will actually show you again the same text that you see on the Jupyter book on the website. And it will open in a Jupyter notebook form here. So this is the one that we looked at earlier. So some of you may be new to what a Jupyter notebook is. And basically a Jupyter notebook is a way to combine text, code, as well as visualizations to see step-by-step how your code is being executed. So it's compared to a lab notebook, or if you're a cook, a recipe book that shows, step-by-step what you need to do, what are the ingredients you need, and what are the results at each part of the recipe. So in a way, working with remote sensing data is similar to that. And so each notebook here will then give you an overview as to which data we're working with. It tells you a little bit more about the data. So in this case, here we're working with Sentinel-3 Ulchi data. And here are some basic facts about the data. 300 meter spatial resolution, global coverage, a revisit time of less than 2 days, and the data is available since 2016. If you're interested in reading more about the dataset, you can simply click here on this link that will take you into the user guide. And it tells you also how to access the data. So in this case, there is a website called the Copernicus Open Access Hub. If you click here, it will take you to this data hub that then allows you to download the data. And you can simply search for the sensing period of your interest. So in this case, because this was an event that happened in 2021, so in particular, August 2021, you can move back to August 2021 and then select a time period. So I will start on the 1st of August and go all the way to maybe the 8th of August. You can then select what data source you want. In this case, we are working with Sentinel-3 data, and you can select the product type here, so OCHI, and in particular, as mentioned up here, we're looking at the full resolution data, so OL1 EFR. So you can scroll down here, OL1 EFR, and just select that. And then you can search. But before you search, you might want to draw a bounding box by clicking here, drawing a box over Italy and Greece, because this will be used to then filter all the images. You then need to log in. So sign up for an account if you don't have one. If you do have one, like me, you can try and log in. I think I might have used the wrong login information. So I might need to reset my password, but basically what you can do is log in and then search, and you will see which images are available for your time period of interest. So that's a quick introduction to how you can download this data. And now we're going to move into the module. So this is the workflow that you can use for accessing, opening, processing, and visualizing Sentinel-3 OCHI data. And we'll be creating both a natural color composite as well as a false color composite. So we begin first in this code cell, which is shown in this gray box here, by loading the required libraries. So I'm going to restart the kernel here before continuing. And basically, I've run all the code already. And basically, when you load a library, you're able to then actually call in all the different libraries that will be useful for what you need to do. So there's some libraries here that are useful for opening data sets and taking a look at the data structure, such as xarray or numpy or pandas. And then there are also some libraries that are useful for visualization. So examples here are matplotlib, cartopy, or this is from scikit-learn, skimage for changing the exposure so that you can see the smoke plumes more clearly. So after we have called in and loaded all our required libraries, we then proceed to load the required functions. And after you load the functions, we can begin to open the data. So the data is located in a data folder. In your directory here, there is a data folder. And basically, if you double click on this data folder, it shows you different folders named from the data source. So data, Sentinel-3, OCHI, 2021, 08, 07. And now you can see that there is here a zip file. And when you download that data from the portal I showed you, it will come down as a zip file. And you need to first import a library called zip file to then unzip it. But we have already extracted the data for you, so you don't need to do that. And now, after extracting, you will see that all this data is available in a different folder inside your original folder. So if we are then to print the various file names inside this folder, you will see that actually all of this match exactly what's been shown here in this directory. So .nc means it's a netcdf file. And as you can see, each channel or each band has its own file. So OA01, OA02, and this contains radiance information. But there's also other types of data, such as the geo-coordinates or the time coordinates. So now we want to load a single channel. And we do that by using xarray.opendataset. And this opens the OA01 radiance channel. And we save this as a variable called OCHI_XR. So when you type this again and you print it and you hit run, unfortunately, there is something strange happening with my Jupyter Hub instance, so I am not able to run the code as I go. However, the results are already here, as I have shown here below. There's basically information about the data variable. So it's the 0801_radiance channel, and you can see some attributes such as the resolution of the data, the start and stop time of this data set, as well as a title, which is the name. So we need to load all the data sets into a single X-array object, and we do this by using xr.open_mf dataset. So this opens then every single band from here into a single X-array dataset. And if you take a look now, instead of just one data variable, now we have 21, one for each channel. And then again, here down here, we see all the attributes. So if you want to plot just a single channel and see what it looks like, you can try simply taking a look at the next box here, this next code cell. And we're using here matplotlib to create a figure. And we define the size of this figure. And then we access the data set with these square brackets from channel 0808. And then we use plot.imshow to plot this data here. And this is what it looks like. However, we want to have this as a georeference image. And so for that, we need the geographic coordinates. So let's again use xarray, xr, to open the data set, which contains the geographic coordinates. So it's geo_coordinates.nc. And then if you print this is what you'll see. It's an xarray data set containing 3 data variables: altitude, latitude, and longitude. And then once again, you have a bunch of attributes you can use later on. Then let's access the latitude and longitude data and save it separately in a separate variable. So lat equals an olchi_geocoords, which is this data set here, and .latitude.data. And then longitude, the longitude data is then saved in a variable called lon, or lon. So to create a true color composite, we have to first select a recipe or the channels that we want to use. So based on what channels or bands you choose, you will end up with very different results for highlighting different types of phenomena. So a true color image is similar to what your eye will see. And basically red, green, and blue, we can then use 08 for red, 06 for green, 04 for blue. And then we use a function that has been predefined called select channels for RGB. And we pass these arguments into our predefined function. So first we tell it the X-array dataset that we want to use, which is this olchi xrmf that contains all the different channels. And then we pass it the 3 names for the red, green, and blue channels respectively. So this is the red channel, this is the green channel, this is the blue channel. These are the channels we're passing in. And so if you print red from here, you will see that, yes, it contains exactly what you expect, 08 radiance, 0808 radiance. And the next thing you want to do is normalize the data. So we will then use another predefined data function called normalize. And this basically normalizes a NumPy array and scales it to between 0.0 and 1.0. And we do this to improve the way the image looks and make it more visible. So we normalize each of the red, green, and blue channels, and then we stack them into a single image stack. And if you take a look at the shape, this is what it looks like. So we know that there are 3 bands in there. And the next thing we want to do is something called histogram equalization. And again, if you take a look before we do the histogram equalization, you see it's quite difficult to see anything because the contrast isn't that good. So this is the result of our RGB composite here, but we want to make it more visible. So we can use the SK image library from scikit-learn that has this function that we can use. So it's exposure.equalize _ adapt hist or adapt histogram. And when we do that, it equalizes the histogram and improves the contrast. So now we can see now there's a plume here from the Evia Islands. So the last part is to georeference it. And to do that, we can use this code here. I notice we're running a little short on time, so I'm going to not go into too much detail going forward. So basically, we create a color tuple by reshaping the shape of this variable called mesh RGB. And then we plot it using visualize S3 p-color mesh. And this takes in a few arguments such as color array, latitude, longitude, and title. You can see what this function looks like here, but you can just directly apply it here too. So we are using the color tuple for the color array, red for the array, the latitude, we pass in the variable lat. For the longitude, we pass in the variable lon, and then we give it a title. And this is our true color image. So for the false color image, it's exactly the same. We just use a different set of bands for red, green, and blue. So OA17 for red, OA05 for green, OA02 for blue. And then we do exactly the same set of steps and we come up with this false color image, which has a very visible smoke plume over here. So that was the entire workflow for our OLCI data. Okay, so I'm going to hop back into the case study here. So if you click that, it will take you back to the point in the case study in this notebook inside our training system. And now if we take a look at fire radiative power, I will be focusing now on the MTG proxy data set. We are using MODIS fire radiative power pixel as the proxy data set. So if you click here on this link in the caption below the image, it will take you to another notebook. And this notebook basically gives you information about the MODIS data that we're using. And one thing interesting to note is that it's a vector data set. So it's not image, but a vector, so point data. It has global coverage, a monthly timestamp, and it's been available since 2000. You can download this data set from firms, and you can choose either shapefile, JSON, or CSV format. And you need to register for an account before you can download this data. So now I'm able to actually run each cell. So if you take a look here, there's a triangle here that looks like the play button. And if you click on it, you are then running or executing the code in the cell. So I've just imported the required libraries. And I'm going to do the same again here with the helper functions. Next, I will proceed to then load and browse this fire radiative power data. And once again, you download a zip file and you need to unzip it before you can use it. So this is the code for you to use if you want to do so, but we've already done it for you, so you don't need to. And inside the zip file, there is a CSV or comma separated values file. And we actually requested the data from the 5th to the 7th of August, 2021. So once you download and open this file, you can actually read the file using pandas with the function read table. And you pass in basically the path name. And because it's a CSV, so we put a comma here as the delimiter. And we tell it which is the index row, which has the header column. In this case, it's the very top row, so it's 0. And which is the column you want to use as the index. So I've chosen to use the 5th column because this shows the acquisition date or ACQ date. Then if you print this data frame which we save as DF, you will see this summary over here has over 2,100 rows and several columns. So latitude, longitude, as well as information about the confidence and the FRP value over here. So I want to filter this data down so that it only contains the latitude, longitude, confidence, and FRP, as well as keeping my index row as the acquisition date. And next, because I'm only interested in the 5th of August, I can then filter my acquisition date column so that it only contains the entries from the 5th of August. So I use this filter and I filter it. So now I only have 785 rows. So because we have a confidence column, I can also remove any entry or any row that has a confidence level below 60%. So using this code here, I'm able to select only the confidence levels which are higher. And now, as you can see, I have even fewer rows, only 650. Finally, I'm creating a color map that basically contains values that determine what each color of each category will be. So as you see here in the final image, there's 6 colors. So blue, kind of a gray blue, yellow, orange, dark red, and bright red. And I'm using these values here to basically state what color each of those categories are. So that's how you define the colors. And I save this as FRP_CM for color map. And then next I have to define the bounds. So the bounds are basically where I want these cutoffs to be for my categories. And I define the bounds and I set a norm for using in plotting later on. And in the final step, because I'm visualizing basically vector data, I use matplotlib's scatter function to initiate a figure. And after initiating the figure, I specify the coastlines and borders. Next, I specify a grid. So this is the grid here. And you can talk about, you can set how far the grid should be apart. And then you can also add some labels or take them away in this case. We set the plot extent to between 10 degrees to 30 degrees on the longitude, and the latitude 35 to 45 degrees north. Then we use scatter to plot the data. And again, we specify the columns that contain our longitude and latitude data to specify where the points are, and that it should be colored by the values from the FRP column. And we should use this color map that we defined earlier on to select the color based on the FRP value. Next, we add a color bar, a title, and then we show the plot. So this is the outcome of this entire workflow. So I've gone through 2 workflows now, and I want to make sure that we also have a bit of time for questions. So I'm going to stop here and open the floor for some questions. And I would like to also welcome Federico and Carla back onto screen to also help out with answering some of these questions.
Yes, hi. Thank you very much. Thank you both of you, Carla and Sabrina. That was great. So I have started to answer a few questions online in Slido. So basically the first one, can we work at the country level for a particular region? Yes, sure. This can be subsetted. Data set can be all subsetted. I think I have put an answer there as well. But I mean, beware of the resolution, because as you have seen, the satellite data sets and all the products have a spatial resolution, so that is at the end the ultimate limit on the usage on a different region. There is a question on the previous seminar regarding fire assessment. I think the link has been posted here. We can also post it again in the chat if you want. That's fine. There is a question on wildfire and clouds. Yes, I mean the clouds, they are they mask most of observation, no, because the clouds are active in the infrared and in the visible. So basically, they emit in the infrared, and once you have the emission of the cloud, you cannot see the emission from the ground as well. This is very difficult to discern. As for the visible, I mean that's obvious. But for instance, if you work in the UV. There is a UV, I mean, the cloud have a more limited effect on the UV radiation. So for instance, what Carla has presented, so the UV index, the UVI index from Sentinel-5P, but also from GOM2. Here let's say I make some advertisement on EUMETSAT rather than Sentinel-5P, but I mean, it's take it as it is. I mean, there is information. You can have information on aerosol, so on the presence of aerosol, also in presence of clouds. So this is one point. I won't go in detail on, for instance, on radar, on SAR, and so on. That can be independent of clouds, because I mean they are not much used, and we're not object here. So I think it is answered that part. I don't know, Carla, if you want to add something, but it's
no, I think it's basically what you mentioned. So to capture hotspot with the presence of clouds, it's not possible because we are using infrared.
Yes.
Yeah.
I mean, one point is that, for instance, you can with a continuous monitoring like geostationary or like MEEO third generation, you can measure, you can survey a region and then find spots between the clouds, no? But sure, when you have a polar system, once it is gone, it's gone. So if you have a cloud, that's it.
That's the real advantage of the geostationary satellite.
Exactly. You can try to spot what happens in the clouds. There was a question on NO2 and CO, I think has been cancelled, right? Yeah, Luigi, from Luigi is below. Is there a way, an algorithm to infer the amount of gases from the total column value? Yes. In fact, yes. I mean, here I imagine that you are talking about the tropospheric amount, no? So that's this is probably the question there. I don't know, Luigi, if you want to clarify or to let's say to target the question, but I mean, I will try to do this. So one, I mean, we say that we have a total value, a total concentration, so a total amount of gas of NO2 and CO, because in fact you measure the level of absorption at the level of the column. Here you have seen the tropospheric column. So it means that there are methods, and that these can be different, to eliminate or to filter by the stratospheric part, what happens above the tropicals. Because, for instance, for NO2, there is a secondary production, there is a production of NO2 that is based to the, in addition to the, yeah, okay, Luigi, perfect. That is produced in addition by the, for instance, by lightning, but also by the more intensive ultraviolet photo dissociation. So basically, you can imagine that you have also a layer of NO2 above. But then what you do, you can measure this, for instance, when you have clouds, when you have high clouds, the satellite measure the total column, the amount of NO2, but measure the amount of NO2 above the cloud. And then this is what you have above the cloud, so what you have generally in the stratosphere. And then you use this, so you subtract this from the total column in order to measure the tropospheric column. In fact, when you look at the Sentinel-5P or the GOM2 and 2 product, if you look at the total column, you have data everywhere, because where you have a cloud, you measure the NO2 above the cloud. Where you, when you have the product on the tropospheric column, you see that this is masked by clouds. But I mean, these are the techniques that are used, in fact. And just to mention, to say something in addition, what is important is, for instance, when we talk about ozone is one of the variables that are most difficult to measure in the troposphere from satellite, because it's an order of magnitude less than stratospheric one, and then it's extremely difficult to filter it. There are techniques that are used similarly at the tropics. So you estimate in the same pixel or in the close pixel what you have above the cloud, and then you use it to subtract and obtain what you have in the troposphere. But I mean, you really eliminate 95% of the signal. For CO is less critical, because CO is really well confined in the troposphere. So basically, it's transported up to the tropopause by deep convection. But I mean, it's generally more confined, and it's really mid-tropospheric species, because it's quite long term. I hope that this answer to the question of Luigi. Okay, and then there are a couple of questions that are more jigs, so more, let's say, technicals. So I leave it to Sabrina, because
Sure. I've been also replying to this on the Slido. Yes. There's basically a set of 4 questions that are basically asking about whether you can use Google Earth Engine to do the same workflows. Yes. And I would say Earth Engine has a number of these data sets. For example, the Sentinel-5P data is also being cataloged by Earth Engine. So take a look at the data catalog, see if the data you want is there. If it's there, you can just access it directly in Earth Engine and use it. If it's not there, then you need to upload your own data into your own asset manager. And the code that we've provided you here doesn't use Earth Engine, so you cannot directly use it, but you can follow the same steps in processing the data if you want. So the answer is yes, but you may need to rewrite some things if you want to actually use the Earth Engine computing power and methods. So that's my answer to the questions.
Okay. There is a question on the total aerosol. So it is important to identify for the water surface reflectance. Okay. Not only for the surface data reflectance, be aware of this, because it's important also for climate, because a different type of aerosol have different impacts, or I mean, to discern among dust and for instance fire plumes, or even dust and pollution. So basically, as you take it, if you measure the aerosol optical depth, you measure an aerosol optical depth. So you measure how much radiation is reduced by the aerosol layer. So we are not able to discern among different aerosol types. But one of the points is that these particles have different dimensions, because they come from different sources and they have a different microphysical history. So for instance, the smoke in general are quite small particles, more spherical, while for instance dust are quite big crystals, are minerals, and also they have a sort of different color. So we have black smoke is soot, is in general black stuff, while for instance other stuff, let's say the dust desert can be more shiny, no? So it's because it can be composed also of mica, of silicates and so on. So basically you can use different channels of observation, because you can measure at different channels in order to have, for instance, a sort of rough signature of the dimension of the aerosols. So if you use different channels, you can distinguish, I mean, without an enormous level of precision among the different topologies. For instance, the Angstrom coefficient that is observed by the aeronet at the ground is used in that way. So basically, you have a different spectral signature due to the average dimension of the aerosol that are interacting with the radiation. And then also what Carla has commented, maybe you want to add something, you can use different visible composition of different visible channels that are more sensitive to polarization effects, because as we say that these particles also have a different shape, and we know that the different shape generate different polarization, so as a change in the polarization of the light. So typically spherical particles, they do not change the polarization of the incident light, while non-spherical crystals, they have a change in polarization. For instance, it's the reason why when you look at the cirrus that are crystals, you can see them, you can more easily see a sort of rainbow effect on them. So they have an effect of halo because they change the polarization of the reflected sunlight. I don't know if Carla, you want to add something on this, but okay. Then how do you integrate with the how you define this, how you integrate GMAP? I don't know what is GMAP.
So GMAP is a Python library that Professor Qiu Shengwu wrote that enables the use of Earth Engine in a Jupyter notebook.
Okay.
And basically this is the same answer. So it depends whether or not the data set is available in Earth Engine. If it is, you can then use GMAP also to call out that data set and visualize it. However, if it isn't, then you again need to somehow upload it yourself into an asset manager. And in the chat, I think Joseph Stevanos said that you have to convert NetCDF to GeoTIFF before you can upload the data. And he suggests using rastereo and Xarray on Python. Okay. So you definitely will need to do some conversion if you want to upload data to Earth Engine from a NetCDF file. Okay. The next question is also covered from our notebook on the MODIS FRP. So basically, the MODIS FRP data contains scan and track information. So you can filter the data based on the scan or the track line number that you are interested in. However, we didn't do that. We instead just specified the maximum and minimum latitude and longitude of the visualization. So only the fires within that window are visualized. So there are different ways to do it. And we have a code that filters the confidence level. And you can reuse this code to filter by scan or track as you need. Thank you.
Last question that goes also to Rosa is also the chance to thank Rosa, that is behind the support EUMETSAT acronym. So Rosa is the course manager. Without her, nothing could have been happened. So thanks Rosa. And yes, the e-certificate. So I think you mean a certificate of attendance. I think we can make this. I don't know. Do you, Rosa, you want to comment on this?
Yes.
Or...
So if you want to receive a certificate of attendance, please just send an email to training@eumetsat.int. So I will then type the email in the chat.
Okay. Probably one recommendation. I mean, request that if you, need
if you attended the course as well, because this will be checked.
If you need it, yeah, because in some way we had 130 people today, and if we need to prepare 130 certificates, it's long. Okay. No, there is another question: how to improve resolution? You want, I don't know, if you want to let's say short and simple. So resolution depends on the if you think about imagery, depends on the dimension of the pixel of the camera that you have on board the satellite, and also on the capability of storage of the data, and also the connection with the satellite itself. So for instance, I can put an extremely resolved camera perfect on the satellite, and then I don't have sufficient bandwidth to download the data. That's also the point. So there are many bottlenecks. But I mean, in general, the improvement of the resolution goes in this direction. So higher signal to noise ratio. So basically, for instance, the need to average on less pixels. The second one on the quality of the imager, if we are talking about the imager, and the third one with the possibility to have a good data traffic. This is for the imagers. If you are talking, for instance, about the spectrometer, so the one that measure the compounds, Carla's mentioned the IASI. IASI, I mean, you work into in 3 dimensions. So you work on the pixel, so on the spatial resolution, but you also work on the spectral resolution. So if I want to have a very fine spectral resolution, of course, I lose in terms of geographical resolution. But for instance, now we are having more and more the technology to have a high spectral resolution, but also going towards a higher geographical resolution. The algorithms are there. Basically, the algorithms are the same. I don't want to open the vase of Pandora of artificial intelligence and of machine learning. I mean, there are, for instance, many. I mean, there are. I'm quite ignorant on this, so it's just the level of knowledge of the typical man of the street, person of the streets. But I mean, for instance, there are approaches and in artificial intelligence in oversampling or in increasing the resolution and the definition of the images. And these techniques, for instance, are also applied to, for instance, to many other imagers, to data sets that comes, I don't know, Sentinel-1, Sentinel-2. There are several works that are published on this. So is a question, is an answer that cannot be exhaustive, but I mean, basically, yes, this is how the resolution is improving. The resolution will be improved more and more. I mean, is one of the keys of the evolution of the satellites. So it is a rolling requirement. But I mean, there are also possibilities, for instance, to aggregate data sets, or for instance, to fill gaps, no, with the AI systems and machine learning. So there are two ways, no. So one is the instrumental, the hardware, and the other one is the software. So if there are no other questions, you may have the chance to throw one very last question, but please do this if you want. I start to close this course. One point, there is a survey. It is very useful for us that you fill it. It takes really no time. It's really very, very, very quick, and we need your feedback, because we need not only to know that we are good, but also to know where we can improve and how we can improve. And I want to thanks again my colleagues, Carla, Sabrina, and Rosa, and really thanks them, and for sure thanks all of you who have attended and had the patience to be with us today. So meet very soon. I think the next short course will be in September. Is that right, Rosa? You have the calendar, no? It's
yes, it's 29 of September, the first short course on autumn, but
okay.
actually the agenda will be defined in the next month. So it's just now there's only one plan ahead.
Okay, great. Do you want to just to share on the fly the yes, the notebook will stay always available. Do you want to share on the fly the announcement, for instance, of the next joint school that we will have with ISA and the CNWF in the chat? So in addition to the short course, we have many other events, many other schools, many other trainings, and part of them they are also starting to be on site or in a hybrid configuration. So keep informed, follow us, follow EUMETSAT, follow Copernicus. I mean, you probably know we are also announcing on Twitter. And yeah, thank you very much. And yeah, this is organized by us, and I mean, here you find all the information and how to enroll and so on. So thank you very much. Thank you, everybody. Keep safe. still keep safe. We are not out of the tunnel, but have an excellent summer for the moment, and talk very soon. Bye bye.
Bye bye.
Bye everyone.
Have a nice
Thank you.
day.